looking at equilibrium conditions under static positions of bodies, we now wish to apply this to a particular structure called truss. These are structures that are used to distribute loads, and you have seen them when you travel. For example, across a bridge you see a structure like this, and here is the road. This structure helps to distribute whatever load there is on the road and takes it to the sides here. This is known as a truss, and in this lecture we wish to analyze the trusses using equilibrium of forces that we have learnt earlier. Another example of truss that you see around is the pillars that carry electric wires that have this kind of structure, and the wires are going like this. These are also trusses. In this case, the structure is essentially a two-dimensional structure. So, these are known as plane trusses, and these are three-dimensional trusses. In this lecture, we will be focusing on plane trusses. Before we start on trusses, I would like to remind you of certain things using the force and torque balance conditions that we have learnt earlier. So, let us see what happens when there are only two or three forces acting on a system. Number one, I am going to look at if there are only two forces. If a body is in equilibrium under two forces F1 and F2, then for body to be in equilibrium, the forces must be collinear and opposite, so that F1 plus F2 is equal to 0. If they are collinear, then about any point the torque also vanishes if they are equal. So, this is the condition for equilibrium. Next, if there are three forces, in that case the forces should either meet at a particular point, so that F1 plus F2 plus F3 not only is 0, the torque due to three forces is also 0. Another way they can provide equilibrium to a body is if they are parallel. So, two forces could act in this direction and the third force could act opposite. In that case, about this point, for example, the torques would be in opposite directions due to F1 and F2, and they will balance out. This is something we are going to use later. Next, a very important thing let me talk about is static indeterminacy. If there is a structure or a body and it is in equilibrium under certain forces and constraints which are holding it together, then if the number of constraints are more than minimum required for it to be in equilibrium, then the system is known as statically indeterminate. If the number of forces, number of constraints are just the number that is required to keep it in equilibrium, then the system is statically determinate. In the case of statically indeterminate systems, the extra constraints that we put which may be removed without disturbing the equilibrium is known as the degree of indeterminacy. This is all illustrated very well with an example. Let us take a rod which has a pin joint at the lower end, and let us say it has weight W. For it to be in equilibrium under this weight, it will have to be supported on this side by, say, a wall, and that is enough to ensure equilibrium, because in this case, if I look at the free body diagram of the rod, it will have a force acting down, which is its weight. There is a reaction in the y direction due to the pin, one in the x direction due to the pin, and there is normal reaction on the wall. These forces are sufficient to bring this rod in equilibrium. Let us see how. So, I have this rod with a pin joint here and a wall here. This has a force R y, R x, a normal reaction due to the wall, and its weight. The equilibrium condition summation f x equal to 0 gives R x equals n. Summation f y equal to 0 gives R y equals to W. Now, about this point, the lower point, let us say the spin joint is O, the torque also must be balanced. If this angle is theta, the length is L, then we have summation torque about O is equal to 0 gives W times L over 2 cosine theta is equal to n times L sin theta, or n equals W cotangent theta divided by 2. Notice that in this problem I have three unknowns, n, R x and R y, and precisely three equations 1, 2 and 3. So, I can determine each and every unknown exactly. This problem is statically determinate. Let us look at indeterminate, corresponding indeterminate problem. If I take the same rod and put a pin joint here and also a pin joint here, in that case this is the weight W. I will have R y 1 and R y R x 1 on the lower pin joint, R x 2 and R y 2 on the upper pin joint. In that case, you see that number of unknowns are 4, R x 2, R y 2, R y 1 and R x 1, and number of equations are still 3, summation f x equals 0, summation f y equal to 0 and summation tau about any point is 0. So, I am putting an extra constraint here by providing a vertical force at the upper pin also. The conditions I get are that R x 1 is equal to R x 2 according to the way we have shown directions, R y 1 plus R y 2 equals the weight, and third condition is the torque condition. You see, all I can determine through this is R y 1 plus R y 2, not R y 1 and R y 2 individually, and this is the degree of indeterminacy. So, this is statically indeterminate problem and degree of indeterminacy is 1, because I can remove this constraint of providing a vertical force and still keep the system in equilibrium. Now, to motivate the trusses, I note 2 points. Number 1, for any point object to be in equilibrium, in general there should be 3 forces acting on it, minimum of 3 forces. And therefore, if I want to make a structure where each joint is in equilibrium, I should provide 3 forces there. There could be 1 external and 2 by something else, or 3 members extending applying forces. For example, let us take a structure where I take a rod and make a pin joint at one end of it, and suppose I want to load it at a particular point. Let me first make a structure of 3, taking 3 rods and provide a pin joint at the circles. Now, you see this pin joint has 3 forces acting on it, 1 by this member, 1 by this member, and 1 external force. So, this can be in equilibrium. However, this joint and this joint are not acted upon by 3 forces, and therefore, to make the structure, make these points come under equilibrium, I have to provide more forces. I could do that by providing one more rod here, which provides 3 forces to this point, and then make one rod here, so that this point is also under 3 forces, and make a joint here. However, the moment I do that, this joint is only under 2 forces. I have 2 choices, either provide a full support here, or another choice, and I will make it in a simple manner now, one joint here, one joint here, one joint here. This is a fixed joint. Here I earlier provided a fixed joint, but now I will put another rod here, another member, and make a fixed joint here. However, the moment I do that, this joint will not be in equilibrium, because this is acted upon only by 2 forces, one by this fixed joint and other by this rod. So, I have to provide one more member to bring this point into equilibrium. The moment I do that, I have one free end of this member here, which also has to be brought into equilibrium. I could provide one rod this way and one rod this way, and this entire structure would be capable of remaining in equilibrium. This is a truss, a plain truss. So is this. So, you see, if I keep making structures like these, I would provide at each point enough forces to keep that point in equilibrium. If I load this structure somewhere, I could load it with some weight here, I could load it here. Each point is now can be brought into equilibrium by forces generated in these members. These members would provide just the sufficient forces to bring this entire structure into equilibrium, and in the process transfer this load onto the fixed supports. This is the job of a truss. If you analyze it carefully, you will see that the number of members that I need to do this is equal to, let me write the number of members equal to m is equal to 2j minus 3. In this case, I provide just enough constraints in the system to make the system statically determinate. If m is larger than 2j minus 3, where j is the number of joints and m is the number of members, let me write it here, m is equal to number of these rods, let us say, and j is number of joints, then the system becomes statically indeterminate. I have provided more constraints than are needed. If on the other hand, so this is statically indeterminate. On the other hand, if m is less than 2j minus 3, then the system is unstable. I have not provided enough members or rods to provide enough forces to keep the system in equilibrium, and therefore, the system may collapse. So, to make it statically just the right number to make it statically determinate, I need m members in a truss with m being equal to 2j minus 3, where j is the number of joints in this. Let us understand how this condition comes about. So, if I take a truss which is externally statically determinate, that means it has 3 constraints from outside. 3 constraints could be in the form of 3 forces, 2 forces, 1 torque, or whatever. So, let us take 3 forces. And then if the number of joints is equal to j, then at each joint if equilibrium condition is applied, then we have number of equations equals 2j, because at each joint, since it is a point, there will be only 2 equations, summation f x equals 0 and summation f y equals 0. And as we saw earlier, with m members, in the truss, there will be m tensile or compressive forces. So, total number of forces is equal to m, which are arising from the members of the truss, plus 3 external forces, and number of equations, equilibrium equations counting 2 for each joint is equal to 2j. If I should be able to solve for all the forces, then the number of equations should be equal to the number of unknowns, which gives me 2j minus 3 equals m, and that is the equation for statically determinate trusses if the trusses are externally statically determinate. So, for externally statically determinate trusses, 2j minus 3 equals m, and that is how we get this equation. Let us see the structures that I made earlier, whether they satisfy this or not. So, let us see, the first structure that I made was this one and the second one was this one. Let us see that. So, the first structure that I made was like this. Number of joints is equal to 1, 2, 3, 4, So, 2j minus 3 is equal to 8 minus 3, which is equal to 5, and I have precisely 1, 2, 3, 4, 5 members. This is a statically determinate structure. The other structure that I made was like this. The number of joints here is equal to 1, 2, 3, 4, 5, 6, and therefore 2j minus 3 is equal to 9, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9 members. So, this is also a statically determinate structure. If I add more rods here, maybe like this, maybe like this, although I am increasing the number of joints. So, at some point it may become a system which is statically indeterminate. On the other hand, if I have less members than 9, then it will be a structure which may collapse. It will not transfer forces in an easy manner or a consistent manner to the sides. You notice that both the ends are put on a fixed point. Actually, this makes the system indeterminate because the number of external forces is now 4. We could make it determinate by putting the right hand side of the system on a wheel or on a roller.